Welcome everyone to another problem session. Today we are doing 2024 JEE Advanced Physics Paper 1 questions. So I'm up to question 6 now. There are 5 questions, there are 5 videos on this channel. You can check them out. So this question is really interesting. This is the kind of question I like because you can do very little work and can get lots out of it. It's kind of, you can just by doing physics intuition, you can answer this question quite easily. Okay, of course you have to know some physics to do it, otherwise you're kind of going in the dark and just guessing. That's no good, just guessing without knowing anything. All right, so we are going to look at this problem from the perspective of just drawing pictures. Okay, so you have a string. Note that the tension throughout the string will be same. So that's very important. It's a uniform tension. That's the key here. So if I have a mass density different, the speed of these vibration waves, which are called sound waves on the string, these waves will be different. So I'm going to call this like side 1 and call this side 2 just for reference. The speed here, let's call it the speed is c1 here, and the speed on this is c2 here. So the speed of a wave, you got to remember this formula. Without, although I'm saying I'm going to do some picture, but you got to remember the speed of a wave on a string is square root of tension over mu. And let me tell you that this way, when you remember it, sometimes you can get very easily confused. You can say, is it T over mu or it's mu over T? And you can, if you're in that camp, how do I kind of check right in this time of test? So I'm going to do, just look at the units. Is this, so tension will be just Newton, and this will be kilogram over meter. So I've got a square root of Newton times meter over kilogram, and you can see already that kilogram gonna have to cancel out meter over second square times meter. Kilogram cancel out, and the whole thing is meter over second. So this is a speed, and if you're keeping track of this, if the sound is going in air, for instance, then the tension gets replaced by bulk modulus, and rho or density replaces mu. So it's going to be bulk modulus over the density for sound of wave. So that's another thing to see. Like one formula you have to remember, and all the other related quantities will give you the same type of formulas. All right, back to the question. So I have this as C1 here, but C2 is saying the tension is same, but mu is 4 mu. So it's square root of T over 4 mu. So this is like a half the speed, half of this speed, which is over here. Now, so that's one thing to notice about speed. Second is the vibration. When string, no matter how many different types of strings are tied together, but they all will vibrate with the same frequency. And the question is why they will vibrate with the same frequency. Why can't it something vibrate over here one frequency and over there another frequency? The answer is to cause the vibration, you have some external agent which is vibrating, and that's the frequency that actually gets transmitted into the frequency of everything. So that's one is the speed. So one was the speed. I'm using letter C for speed, not V. And second is the frequency, which these people are using nu, and you could use F. This is the Greek letter nu. That's also common. Okay, so this will be same. So this tension was same. Tension is same throughout, and frequency is same in both parts. So what will happen is the tension is same, but C is different. Frequency is same. And the third thing to get from our memory is the for any wavelength, or like over here, have a whole wavelength versus over here, any wavelength that I'm going to have. So wavelength on the first strings, let's call lambda 1, I'm going to have, then the frequency will be the same, right? So just use this 1 or 2, doesn't matter, just nu for that, will be equal to C1. You can see that for the same frequency, you'll have different wavelengths because you have different speeds. So you have same nu, say I have same nu, then this will be 1/2 C1. So you can see that if I have the same frequency, the wavelength over here is double the wavelength over here. All right. So from here we got this very important information. Same nu, for same nu, wavelength on 1 is 2 times the wavelength on 2. So this will be our rule, and we're going to draw some pictures, and then that will be give you a very cute way to solve this problem. I forgot, when you draw the pictures, you should remember that when a string is tied, you're going to have a node there. Okay, so let's draw answer question A with a node at O. So it's saying whatever you're going to draw, you put a node at O. So we got several places already that tell you what to do. So you have a node here and a node here, and this is L, and this thing, I guess I should make it over here because just 2L. So this is 2L, and so these are P and Q. They will be nodes. The minimum frequency of vibration will be what try to fit waves here, right? So over here there has to be node and node. So the only thing I can fit in here is just this. So this is like a lambda for this is going to be this only half the wave, right? So half the wave is fitting on L, so lambda 1. So that just tells me a lambda 1 equals to 2L. Okay, now from here I already know lambda 2 has to be half of that, so lambda 2 has to be L. So let's see if I can fit in with node here and continue to the string. So string will have to continue in that way. Oh, I should use a different ink, and has to be full wavelength. So it turns out to be full wavelength is a lot. It will be like that, but this is going to be wavelength of 2L if I want to fit like that. So that's not what I want. I want a wavelength to fit in this and another wavelength to fit in that. So what I would need is go this way, go this way, not the green one. So the green one is not, but this will satisfy, right? The green one is the blue one that I need. So that's with a node O, minimum frequency of vibration will look like this. So we can see that with a lambda equals to 2L, lambda 1 equals to 2L, and C1 is equal to, we just wrote down over square root of T over mu, then frequency will be, nu 0 will be C, and for this particular mode, it can look like this. So C1 is square root T over mu over 2L, which is, this is nu, and then this same as mu 0. So this is correct, actually. A is correct because of this reason. This mode, which is the least longest wavelength or minimum frequency, will be look like this, just from drawing the picture. All right. The B is saying that if you try to do an anti-node over here, not node, then you'll have a frequency 2 nu 0. We have to check that. Let me pause. Okay, I'll clean that, and let's redraw this picture. So for B, I need to draw a different kind of picture. So this is L, this part, and this part is 2L. This is L. So it says try to fit the longest wave. So, but you got to be anti-node over here. But of course, these guys have to be node. So if I try to fit it like that, then this is only quarter of a wavelength fits. So only quarter of a wavelength of this type, lambda 1, is L. So this kind of thing will have to be lambda 1 has to be 4L. And we already know C1 is square root T over mu. Then frequency corresponding to this lowest one, so whatever, let's not put anything, just call it nu. Nu corresponding, this is going to be C1 over this lambda 1, and this is about 4L square root T over mu. But that is 1 over 2 nu 0. It's going to make sense, the wavelength doubled, the frequency has to be half. But this problem is, this answer is saying no, the frequency is double, which is of course not going to happen. So that's pretty easy to knock that one out. That's wrong. And for C, I just erased the picture, so I'm going to redraw the picture. The picture for A is what it's saying, what it looked like. Picture for A was, you had a node here and a node here and a node here, and there was one wavelength here and another wavelength here. So it was like this, like that, and this thing went this way. So if it's saying count the number of nodes, okay, it has 6 nodes. So 1, 2, 3, 4, 5, 6. So this is correct. Now I'm going to show you why D turns out to be a problem. Okay, so we already saw that anti-node had a problem over there, but what happens in the D? Okay, I'm going to try to do anti-node. It's kind of like this, right? So we try to do anti-node on this side, and then we'll have to do anti-node on this side also, right? So this can be, the question is, if I do something like this, what happens over here and over here? Is it possible for any vibration to kind of have this kind of shape? And we also know that over here in this part, if this is lambda 1, then whatever I'm going to get over here, lambda 2, has to be half of lambda 1. So let's look at the conditions, what the conditions will be on this side. This side is going to be 4L over any odd number, so 2n plus 1. That's how it can fit here, right? the wavelength over here. So lambda 1 will have like this, and lambda 2 will have similar formula here. It will be, the length of this is 2L, 4 times 2L over some other set of numbers like that. And the question is, are these numbers compatible? So lambda 2 is supposed to be, because of this, lambda 2 is half of lambda 1, right? Lambda 2 is supposed to be half of lambda 1. Let me check that out. So if I put this over there, you are going to get 8L over 2m plus 1 for some m, and some n is going to be half of that's 2L. So this 4, let me see if my calculation that are early. Okay, so if I carry it forward, let's see if where does it go. So I have this. Is this allowed for some m, some n? Just cross multiply it. So I got 8n plus 4 equals to 2m plus 1. So let move this side, move this other side. I get 2 times m minus 4n equals to 3. So this is an even number and this is an odd number, so not allowed. There will be no mn like that, so this t has to be wrong. Okay, so let's recap lessons we can learn from this, what things you should know before we can actually do this problem in this fashion. There are other ways of doing this problem, but I just prefer this one. So one is the speed formula you should know, and you can also know that speed of wave on different strings which are tied together would be different, and as a result, but the frequency will be the same. So this is very important. So this formula is important, and that the frequency will be same, and these other things is a consequence of that. So over here you can see that this, you have a much wider wave, and then with a much tighter oscillations on the more massive string, and this is actually a very common thing. So this picture is also kind of important to keep in mind. I knew what to expect actually before I even started this problem. So I knew this is going to be more oscillations here and less oscillations over on the other side for the same frequency. Okay, so that's all for now. I'll see you in another video. Bye.